Today we're going to talk about exponential functions. Okay, so normally what we know about exponents is that we have some number that's a base, we raise it to an exponent, and then we get our answer. So now we're going to talk about what this looks like as a function. Here's my answer. My answer is f of x, or a y. I still have b as my base, and x is my exponent. This a is just a multiplier like we have with any of our functions, like we just learned about polynomials. And I can have horizontal shifts and vertical shifts as well with this function, and that's where they'd be placed. I can have reflections over the x-axis and y-axis, all things that we know how to do from chapter 1.8 from transformations. So looking at this graph over here, this is kind of our parent graph of f of x, and it's very general. So right now, this is the graph without any transformations applied to it. We have three interesting points. We have this point -1, comma, a divided by b. We have another point 0, comma, a. And we have another point 1, comma, a times b. So this is only for a graph, an exponential graph that doesn't have any shifts, horizontal or vertical, or reflections. We'll talk about how to find these points when we do have those transformations. They'll just follow the same transformations of f of x, so we'll just convert those points themselves. So looking at this graph, our domain, our x value, it continues forever. I know this looks like it goes up and there might be some like asymptote, but truly, we can plug in any value for x. Any value for x will give us a true value for this function. So any of these x values are valid. So I'm going to write in domain, I'm going to write -infinity to +infinity. Now our range is where it gets interesting. No matter what I put for x, as long as my a is positive, no matter what I put for x, I am never going to have a negative y value. So I have this horizontal asymptote at y equals 0. So I'm going to write that down, horizontal asymptote at y equals 0 here. So that means my range of just this general graph is 0, not including 0, all the way to +infinity. So if we did, the only way that we could have a horizontal asymptote move or our range change is if we had a vertical translation up, a vertical shift up, or a vertical shift down. Our x-intercept, again, since we have a horizontal asymptote on the x-axis, we don't have any x-intercept right now. We would have to have a vertical shift down in order to have an x-intercept. But our y-intercept, that's at the point 0, comma, a, as long as we have no other transformations. We have this shape. It is always increasing. No matter what we're doing, we're always getting bigger. We're always increasing. Now, if we had a reflection the other way, like this, that would be decreasing. That would be a decreasing function, and our a value would be negative there. Okay. So now let's go ahead and let's try graphing f of x equals 2 to the x power. So I'm going to go ahead and note that my a value is just 1 and my b value is 2. I don't have any other transformation, so I'm just going to use those 3 points we just talked about to plot this graph. So I know I'm going to have a point at -1, comma, a over b. So for me, that's at 1/2. So I have this point here, -1, comma, 1/2. I'm going to have a point at 0, comma, a, and our a value is 1 again. So I have that point at 0, comma, 1. And then I'm going to have the point at 1, comma, a times b. A times b is 2. So I've got this point here at 1, comma, 2. I know that I'm going to have a horizontal asymptote at 0 since we're not vertically shifted at all. So I'm going to hug the x-axis. I'm going to hit those points, and I know that I finish my function with an increasing trend like that. So that's all I've got to do for this problem. My domain, we already talked about. This is all real numbers so far, from negative infinity to infinity. We have a horizontal asymptote at y equals 0, so our range goes from 0 to positive infinity. Our x-intercept, none. Our y-intercept is 0, 1 here. And because our a value is positive, it's positive 1, we are increasing the whole time on this function. It is going upwards. Okay, now comparing what we just had with the graph below, 2 to the x minus 3, what I know about transformations is that this function is the same as the graph above, it's just moving to the right 3. So what I'm going to do is I'm going to take all the points I just found, that negative 1, comma a over b, 0, comma a, and 1, comma a times b. All I'm going to do, so I would find those points first. If I was graphing this without graphing the one above, I would find those points first, and then I would just shift them over 3 in their x coordinates. So that point, negative 1, comma 1/2, I'm going to add 3 to my x value, and that's going to move me over to positive 2, comma 1/2. And then 0, comma 1, again, I'm going to add 3 to my x value. I'll get 3, comma 1. And that point 1, comma 2, when I add 3 to it, I will get 4, comma 2. So, okay, let's graph those points. I have 2, comma 1/2. I have 3, comma 1. And I have 4, comma 2. So this is the same exact graph. I didn't have any vertical shifts, so I still have that asymptote at y equals 0. And then I'm just going to follow the points, and I have my increasing trend. So this is the same exact graph, just shifted to the right 3 units. So my domain, still negative infinity to infinity. My range didn't change. I still have a horizontal asymptote at y equals 0. I don't have an x-intercept. To find my y-intercept, I'm going to plug in 0 into x. So we've got 2 to the 0 minus 3, and I can simplify that. That's 2 to the negative 3rd power, which is 1 over 2 to the 3rd power. So if you're having trouble understanding what I just did there, make sure that you're watching some intro to exponents or solving exponents on YouTube, on Khan Academy, because I'm already expecting that you know what a negative exponent means. So that's going to simplify to 1/8. So this little point right here is going to be 0, comma 1/8. Our function is increasing. Okay. We're going to do some more graphs that have a different a value than 1 to see what happens. So now we've got 3 times 2 to the x power. Okay, so we're still going to follow the situation. My a value is 3, my b value is 2. So at negative 1, I should have a point at negative 1, comma 3 over 2. That's my a over b, so that's about 1.5. It's right here. At 0, I should have a point at 0, comma a, so that'll be 0, comma 1, 2, 3. And then at 1, I should have a point at 1, comma a times b. A times b will be 6. So this point will be up here. 1, comma 6. Again, I don't have any vertical shift there, so I still have that asymptote, horizontal asymptote at x equals 0. I'm following through my points and ending upwards. So my domain here did not change. My range here did not change. My horizontal asymptote did not change. My x-intercept, again, we don't have any because we don't have a vertical shift. Our y-intercept is easy to see. It's 0, comma 3. So we are increasing. I kind of have to graph the function in order to see what it looks like to figure out if we're increasing or decreasing. So looking at my function below, we've got a reflection over the y-axis. That's right here. I see that right here. Reflection over the y-axis. And then I have a vertical shift up 1. Okay. So what I'm going to think about is all of these points, I need to flip them over the y-axis. So that will make all of my x values negative. But I will keep the same y values. So I'm going to go ahead, and that means that this point, -1, 3/2, if I'm flipping over the y-axis, that means I have a point at 1, 3/2. This is just my reflection so far. I'm not including my vertical shift yet. At 0, 3, if I just change the x value negative, that's 0, so that doesn't help me. Or it just doesn't change, right? -0, +0, same thing. And then I have my point 1, 6, but that's going to flip over the x-axis or y-axis to -1, 6. Now, we're not done. I didn't take into account my vertical shift up. So that means my y values are going to go up by 1. So I'm going to have 1, 3/2. So that's about 1.5. So if I add 1, that will be 2.5. I'll have 0, 4, and I will have -1, 7. So I can go ahead and plot those values. 1, 2.5, 0, 4, and then -1, 7. Okay, so I also need to pay attention. Since I had a vertical shift of +1, my horizontal asymptote also moves. So that means my horizontal asymptote is now at y equals 1. Okay, so I'm going to write that down here. My horizontal asymptote is now at y equals 1. So I'm still going to connect the dots, and this is going to be a decreasing function. I'm going to hug the x-axis here. Maybe you'll be able to draw a little bit better than I will. But this is our same function we had above, reflected over the x-axis or y-axis and shifted up 1. So our domain did not change, still all real numbers. Our range did change because now our horizontal asymptote is at 1, so we're not going below 1. Our x-intercept, again, we have none. It will never go below our horizontal asymptote, so we're never going to have an x-intercept. Our y-intercept is right there at 0, 4. Forget about the a thing. I don't know why I wrote that. I forgot what I made it stand for. But our function here is decreasing always, decreasing. And we're always going to be going down. Okay, we have 2 more graphs here. 2 more graphs. Okay, this one, I've got an a value of 1/2, a b value of 2. I've got a shift right by 2, and I've got a shift up by 3. So I'm going to go ahead and find those A, B points, and then what I'm going to do is I'm just going to add 2 to my x's and add 3 to my y's. Super easy at this point. We've got the procedure down. So my A and B values are -1, A over B. So it would be 1/2 divided by 2. What I know about fractions is that would be 1/4. You can do the math out if you need to. 0, A, so that will be 0, 1/2. And next I will finally have 1, A times B, so that would be 1, 1. Okay, but I have to take into my account my +2 on my x's and my +3 on my y's. Okay, so I'm going to go ahead and add my 2 and my 3 to the x and y coordinates. I will get 1 comma 3 1/4, 1 comma 3, 2 comma 3 1/2, and 3 comma 4. Okay, let's go ahead and plot those points. 1, and then I'm going to guesstimate 3 1/4 is there, 2 comma 3 1/2, just a little bit higher, and 3 comma 4. Okay, so because I shifted up 3, I know that my horizontal asymptote is right at 3. I'm not going past that. So my graph is going to hug that asymptote and hit all of my points and end upwards. It is going to have a domain still of all real numbers. My range will be 3 to infinity because my horizontal asymptote is at y equals 3. My x-intercept, I will not have one. My y-intercept, okay, I could solve that again by plugging in 0 for x. When we do that, I get 1/2 times 2 to the 0 minus 2, which is just minus 2 power plus 3. Okay, so that'll be 1/2 times 2 to the negative 2 is 1/4 plus 3, which will get me 3 plus 1/8. Okay, so it's going to be 3 plus 1/8 at that spot right there. So 0 comma 3 1/8. And then again, I am increasing because I can tell by my points. Okay. Lastly, I have f of x equals e to the x. So e as a number is like 2.72 we'll use as a rounding number. So I'm not even going to calculate the exact numbers here. I'm just going to guesstimate. So I'm still going to I have no other transformations, right? I don't have any a value, that's just 1. I don't have any shifts up or down or any reflections. So I'm going to have that point, -1 comma a over b. My a is 1 and my b is this 2.72 value. So 1 over about 3, that's about 1/3. I can estimate 0 comma a, so that will just be 0 comma 1 since my a value is 1. And then 1 comma a times b. So my a is 1 and my b is e, so I will have these points. I could label it if I was labeling it on a graph. Well, let's do this. So this is about -1 comma 1/3, but I could label this -1 comma 1 over e to make it easier and make people know, oh, this is e, not just some random number. 0 comma 1 happens here, and 1 comma 2.72, almost 3. I can label that as 1 comma e. Again, my horizontal asymptote did not change. It's still at 0 because I don't have any vertical shifts, and my function is increasing. So we've got domain from -infinity to infinity, my range from 0 to infinity, my horizontal asymptote at y equals 0, my x-intercept, I already have that. I'm not going to have an x-intercept, but my y-intercept is 0 comma 1, and my function is increasing. Okay, we have a few more things to go through. Exponent rules and properties again. So I'm not going to review the exponent rules, what happens when you're adding things like this, multiplying, dividing, have an exponent with another exponent. That is all things that you learned in Math 1 and 3. So review those on your own if you need to. I highly suggest it. And now we're going to talk about one-to-one solving. This is a new property of exponents we're learning. So if I have some base, if they're equal to each other, then their exponents must be equal, right? I can't have 3 to the 4th equaling 3 to the 5th. We know that that does not work. So we know that this 5x plus 2 has to equal 12. So I can just kind of ignore the bases and bring down my exponents and set them equal to each other. But again, this only works if the numbers on the bottom have the same base. So I'm going to continue to solve this. 5x equals 10, and I get that x equals 2. Perfect. Now, the one below this, 9 equals 3 to the x plus 1 power. Right now, these do not have the same base. However, I'm going to think about how can I write them in order to have the same base. Well, I know that 9 is just 3 to the second power. And I'm going to keep my 3 to the x plus 1 power over here. And now they have the same base of 3. So I can set my 2 equal to x plus 1 and solve for x equals 1. Okay. This one might be even harder to see. I have 1/3 to the x power equals 27. So I have 1/3 to the x equals, and so I want this to have a base of 1/3. 1/3 to the what power would equal 27? So let's think about that. 1/3, no matter how many times I multiply by itself, it's going to keep getting smaller, right? 1/3 times 1/3 is 1/9. It's going to keep getting smaller because I'm just multiplying fractions by fractions. So I know that I need a negative exponent here to flip this, to flip 1/3 to be 3. So if I have an exponent of -1, that number now becomes 3. How many times do I have to multiply 3 by itself to get 27? The answer to that is also 3. So my exponent here is -3. That means x equals -3. Okay. And then we also have some word problems, some applications. So we have half-life. That is really exponential decay. So that's when we have a decreasing function that looks like this. Our problem says there are 10 grams of curium-245, which has a half-life of 9,300 years. That means, so I have 10 grams. My half-life is 9,300 years. So that means it takes 9,300 years in order for the amount of this compound to cut in half. So every 9,300 years, we multiply by 1/2, right? It'll take another 9,300 years for us to end up with 2.5 grams. Okay, so I don't want to keep doing that until I reach 37,200. I want to make an equation to help me solve this. So I know I'm starting with 10. This is going to be my A value. Now we're going to multiply by 1/2 many times over again, right? We're multiplying this number by 1/2 here and by 1/2 again. So that's kind of my B value. My exponent is going to be how many times I'm multiplying by 1/2. So when we're thinking about how many times I'm multiplying by 1/2, that will be our entire time length divided by our half-life, by how long it takes us to divide by 1/2. So I can also think about this as how many half-lives will I have in 37,200 years? So I can do that math separately, or I can just write the math up here in my equation. Okay, so that's like my exponent. I'm going to just simplify this. Remember, we have to do exponents first, so I'm not multiplying the 10 by 1/2. I have to do my exponents first. 37,200 divided by 9,300 simplifies to 4. So I will now have 10, and then I'm going to distribute my exponent of 4 to the top and bottom of that. That will get the fraction 1/16. And I multiply that out, and I get 0.625 grams will be remaining at that time. So this is our exponential function here. We kind of have our original amount times our half-life, or our decay or growth, to some time frame. Okay, so kind of use that structure as you're answering problems like this. We're going to learn 2 more equations that are helpful here. Heather received $200 for her 13th birthday. If she saves it in a bank with 3% interest, okay, I'm going to remember that 3% is 0.03. Compounded quarterly, that means 4 times a year. How much money will she have in the bank on her 16th birthday? Okay, from 13th birthday to 16th birthday, that time is 3 years. Okay, we're going to use a compounding formula here. Our compounding formula, A equals P times 1 plus R over N times T. Okay, so A is our total amount of money. P is our initial amount of money. So in this problem, our initial amount of money is $200. We have this 1 here. If it's growing, we're going to add. If it is decaying by a certain rate, we are going to subtract. So here we're going to add because we're growing money. R is our rate, so that's 0.03 because we're going to use decimal form. And our N is how many times this is compounded per year. So for us, that would be 4 times per year. In our exponent, again, we're going to have that same value for N. And then we're going to have T, which stands for time, how many years. So for us, that's 3. Okay, I'm going to go ahead and simplify this. I will get 200, so I'm going to leave that there because I need to deal with my exponents and stuff in parentheses. First, 1 plus 0.03 over 4 is 1.0075, and then 4 times 3 is the 12th power. So then I'm going to multiply, or I'm going to put 1.0075 to the 12th exponent, to the 12th power, figure out that number, and multiply times 200. And my final answer is that on her 16th birthday, she will have $218.76. So that's compounding so many times a year. We have quarterly, where our N value is 4. We can have monthly, where our N value is 12. We can have semi-annually, which is twice a year, so that our N value would be 2. Okay. Now we're going to talk about compounding continuously right here. Compounded continuously. So this is where that value E comes in. Our formula for anything that's compounded continuously is A equals PE to the R times T. So that natural number E, that 2.7, helps us calculate interest compounded continuously. So not much is going to change though. P is still going to be what we start with, $1,500 into an account earning 7%, 0.07 annual interest. So our E, that's not a variable, that represents 2.72. And then our rates times our time, which is 4 years. That's the time in years. Again, I'm just going to go through, plug that into a calculator. I'll have to do 0.07 times 4 first, then raise E to that exponent and multiply that whole answer by $1,500. I'll get that I have $1,984.69 in my account. But that's the total amount. To find out how much interest was earned, I subtract what we call the principal, which is what was in the account initially. When I subtract that, I find out that my interest, I'll put int, equals $484.69. All right, hopefully you know a lot more about exponential functions now.